Dear student, hello. I have the pleasure to share with you a course about free and damped oscillations of systems with 1 degree of freedom. Here is the most basic system making free and damped oscillations with 1 degree of freedom. What does it mean free? It means that the system, we didn't put any force to the system in order to help or assist it, but the system is oscillating with its own forces. And undamped means that we didn't put any damper able to vanish or to stop the oscillations. So we can directly make a conclusion that such system is an unrealistic one, because even we didn't put the damper, we have the air friction, which are natural damper, and they are able to stop the oscillations. Here are different examples of systems. And here let me explain to you what happened physically in such systems. At the beginning, at equilibrium position, the characteristic of this position, and it is U equal minimal, potential energy is minimal, and we can modelize it mathematically by the derivative of U over d theta equals 0 for theta equal theta equilibrium, and in our case theta equilibrium is equal 0. You have to take it by heart that the characteristic of equilibrium position is potential energy minimal. It is physical characteristic, and mathematically modelization is the derivative of U over theta equal 0. When we pull upward this system, it means we have disturbed the equilibrium. It means also that we gave to it an excess of potential energy. And we release this system, and the system will regain its equilibrium position. So it regains this equilibrium position by losing the potential, the excess of potential energy, and the loss of potential energy will be converted to kinetic 1. So as conclusion, that at equilibrium position now the system can't stay at this equilibrium position, because the kinetic energy is not 0 anymore and it has velocity. So in order to cancel this velocity and this kinetic energy, it tries to continue its path in the other side, and during this path the kinetic energy will be converted to potential 1, and it will encounter the same problem as previously, and the system finds itself being in motion of back and forth, as it doesn't stop, yeah, and it will oscillate indefinitely. That's why I said to you that it is a realistic system. Our system is this one. It consists on small mass m, dimensionless. It means without dimension, and attached on at the end of a rod with mass capital M and length 3L, and we have attached two springs, K1 equal K and 2K, and K2 equal to K, and that is the main questions are find the differential equation of motion and find the equation of motion. To answer the first question, we have to follow steps, 5 steps. The first is kinetic energy, the second is potential energy, the third is quadratic form of potential energy, the fourth is Lagrangian, the fifth is equation of Lagrange, which leads to the differential equation of motion, and then the resolution of differential equation of motion leads to equation of motion. Let's go with the first step, which is kinetic energy. First of all, for kinetic energy, we have to count the number of masses. We have two masses, hence two kinetic energies, Tm plus T capital M. And each kinetic energy can have, in general, two kinds or two types or of kinetic energies, translational plus rotational one. Now, for the small m, it hasn't dimension. When we have mass without dimension, it is forbidden to speak about the rotational energy. So, Tr equals 0. And for the road, yeah, it is, if we consider our study about the real axis, here the real axis of rotation of the bar passes through O. In this condition, we can say that T translational equal 0, because there is another method, but it's sufficient to know this one. Another method is conic theorem, but it's sufficient to know this method. This is the method of axis of rotation. Now, the translational kinetic energy of the small mass is equal half m v square, velocity square, and because it is translational, half m v square, and the v is equal the derivative of the curvilinear abscissa over the time, and you see the abscissa S or the displacement S, you see here it's curvilinear. Even it is curvilinear, it doesn't mean, and the theta you see, and you see that the generalized coordinate is theta, it doesn't mean that we have motion of rotation. No, we have a motion of translational curvilinear motion. Okay? And you see, because it's not about theta, it is about the mass. It hasn't dimension. It means it hasn't inertia moment. Okay, it has only mass, and so the kinetic energy is translational one. It's equal half m v square. So sorry. You see here that S is equal to L theta, and by replacing we get this expression. Now for the rotational kinetic energy for the road, the capital M mass, it is equal to half E0 theta point square. It is rotational kinetic energy. So in rotational motion, the parameters which resist to the motion is not m anymore, but it is the moment of inertia EO. Here the E, it's moment of inertia about an axis passing through O. We have to calculate it, because what do we know? We know in tables, it's put in table, the moment of inertia about an axis passing through the center of the mass G, and it is known, and we can take it from tables for any geometrical shape. Here our geometrical shape is it's a road, so it's equal to 1 over 12 m, the length, the total length of the road, to L square. Now, in order to calculate EO, we use the parallel axis theorem or Huygens theorem. EO is equal EG plus m times the distance GO square. By replacing, we get this expression of EO, and we replace in TR, we get this expression. The total kinetic energy is the summation of the two energies, kinetic energies, and we get the expression. Second step is about the potential energy. The potential energy, we start like this: U is equal U gravitational plus U elastic. And now we deal with U gravitational potential energy. First of all, we have to count the masses. We have two masses, so two gravitational potential energies. Okay, and each one is equal plus or minus mgh. What is the h and capital H? H and capital H are the distance, the vertical distance between the current position of the mass and the reference. So here we have, for gravitational potential energy, we need always a reference. Okay, and just for gravitational potential energy, a reference, I have taken it in the equilibrium position, as you see, but you can take it elsewhere. Okay, it's not false, but I always advise my students to take in the equilibrium positions is better. So the H is this one for the little mass, between the mass and the reference, between the point mass and the reference. And for H, it is a rod. It has a lot of points. So when we have a solid mass like this and we have a lot of points, the distance will be between the center of the mass and the equilibrium and the reference. Okay, so now here we need to calculate H and capital H. You see in the picture that H is equal to L sine theta, which is equal to 2L theta because theta is very small, and in these conditions the sine theta equal theta and cosine theta equal 1 minus theta square over 2. The capital H is equal L over 2, as you see in the picture, sine theta. By replacing in the expression of the gravitational potential energy, you see for the first mass is equal plus mg2L theta. Why plus? Because the mass is above the reference. The same thing for capital M. The mass is above, the center of the mass is above the reference. And the result is this one. It's worth it to notice that U gravitational is with respect to theta and not theta square. It means that U gravitational in our case help to make equilibrium and not oscillations. You see, I will explain more and more after. You see that because we have equilibrium position is horizontal. When the equilibrium position is horizontal, the gravitational energy can't help the oscillating. It helps only to compress or stretch the springs in order to make theta equal 0 at equilibrium position. Okay. Now the elastic potential energy is about the springs. We have two springs, so two potential elastic potential energies. Okay, and the first we have the first for the first spring we have half k1 x1 plus x0 1, and you see in the picture that the spring k1 is stretched, elongated. It means that x1 is equal plus, and for the second you see that also the x2 the spring is elongated, so you take plus. If it is compressed, we take minus. Okay, and the calculation of x1 is L theta, x2 is L theta. x01 and x02 are the deformation of the springs at equilibrium, and here it they don't appear on the picture, the x01 and x02, because they are elongation or deformations in general. It can be compressions of the springs at equilibrium. That's why I will explain in the next slide separately, and I give you one scenario because there are other scenarios. My scenario is this one. You see that at rest k1 has a length natural length, and K2 has natural length, and by putting my masses here, and I aim to get the theta equal 0. It means the K1 will be compressed with the distance x01, and force is generated by the spring K1 in this direction, and here we risk to lose our theta equal 0 at our equilibrium position, because this force will rotate the masses in upward around O. Fortunately, we have this spring K2. It can be elongated. It can with the distance x02, and here you see that it generates this spring K2 is generating a force attracting or making the balance of the system in order to get the equilibrium position at theta equal 0. I would like to say that you see that x01 it is the K1 is compressed and the other is stretched. I mean that don't care about the sign of x01 and x02. You can take them directly positive, okay, because there are other scenarios, okay, and what is important here is the relationship between x01 and x02, because there are other scenarios. Okay, we can in other scenario find x01 positive and x02 negative. I mean that let them with positive, and that is, you see that we add here x01 plus x02 plus, and we develop and we get this expression with C equal this expression. Now it's worth it to notice that U elastic is equal half A theta square plus B theta plus C. What we need here for oscillations is the term of theta square. It is the quadratic form. The B here is not needed in our oscillations. We need it to equilibrium position, position situation. For U, you see U gravitational plus U elastic, U total, we have this expression. Okay, you see it's the same thing. U total is a term A theta square plus B theta plus C. Okay, it's the same remark. The half A theta square is a term needed for oscillations. It can be converted to kinetic energy, etc. But B, you see that just characteristics of, you see here, the relationship between characteristic at equilibrium, and you see our masses enter in theta, not theta square. It means in this situation, when the equilibrium position is horizontal, the G can't play a role of oscillating. Okay. Now, since the main important term is half A theta square, we need to cancel the B theta and put our U in its quadratic form. That we will see in the next slide. So the third step is quadratic form of the potential energy, and we use the condition of equilibrium. The condition of equilibrium, I explained it already. Du over d theta equals 0, and our expression of U total, I derivated, and I get this, and I replace the theta with theta equilibrium, which is equal 0 in our case, and I get this expression. You see, it is the expression of equilibrium condition, of equilibrium condition. You see that we have a relationship between the parameters at the equilibrium. I remind the U. So I have the condition of equilibrium. I put it 0 in the U, and hence I get the quadratic form of our potential energy. Our potential energy must be in terms of theta square, with respect to theta square. I don't need theta. Okay? So this condition of equilibrium, it's very, very important, because it is making the potential in potential energy in its quadratic form in one hand, and in the other hand it gives the relationship between the characteristic of the system at equilibrium. The Lagrangian L equal kinetic energy minus potential energy. A lot of students find that it is strange to speak about T minus U, because they know T plus U. It is the mechanical energy T plus U. But here it has a meaning, a deep meaning, because T is relevant to velocity and U is relevant to position. And you see, when T is greater than U, it means the motion, the system has a motion over than stability, and the opposite thing we can say when T is small relatively to U, the system is not in great motion. Here the fifth step is equation of Lagrange. Equation of Lagrange, we write it like this. Okay, we don't need a demonstration, but we need only how to use it. Because if you want a demonstration, there is a book of Jilwah. It is well explained inside. The derivative of L over theta point, we will derive only the kinetic energy, and we derive again about T. So theta point is theta 2 point. Now dl over d theta, we derive the L over theta, and we get the expression. Omega 0 is equal, this expression is the natural angular frequency of the system. Now theta 2 point plus omega 0 square theta equals 0 is the differential equation of motion. We get it. Now the second question is the solution of the differential equation of motion. You see, the solution is directly given by a cosine omega 0 t plus phi. If you want a demonstration, you can see a mathematical work or demonstration of differential equation of motions. Okay. Now, A and phi are the maximum amplitude and the initial phase, respectively. Sorry. I'm sorry. In order to determine A and phi, we need the initial conditions. Sorry, here t at t equals 0 t, it's little t, not capital T, to say that it is time. Theta is equal to degree and theta point is equal 0. So we need theta point by derivating the theta, and we replace in the first the initial condition in the first and in the second, and you see that in the second we can get phi equals 0 or pi, and we have to choose one of them. We choose the one that verifies the equation 1, and here it's phi that verify the equation 1, because the A must be always positive, and by replacing in our equation we get this equation in and it's the equation of motion. You see the difference between the differential equation of motion and the equation of motion is that the differential equation of motion is a relationship between the generalized coordinate, the generalized velocity, the theta point, and the generalized acceleration, theta 2 point. But the equation of motion is the theta with respect to t. That is. Now, I would like to show you when we make rotation of the system with an angle equal to pi over 4, what happened? You see? Here, nothing will change. Nothing. The kinetic energy will remain the same. The potential elastic potential energy will remain the same, but the I said the elastic potential energy remains the same, but the gravitational potential energy will change. You see? We write the equation of the expression of gravitational potential energy, and you will see the difference between this age and the age previous age. You see that we have to take a reference. Here the equilibrium position is vertical. Previously it was horizontal. Okay, it makes a great difference. Here the reference for the first mass, and here the current position, and here we have the distance between the reference and this current position, and you have here the h is the green one instead the red one. Okay, when we calculate it, we will get 2L minus 2L cosine theta, and because theta is small, we can write it like this. For the second mass, we follow the G. You see that at equilibrium it was here. By the way, we can take different references. Okay, for each mass we can take its own reference. So I take this reference, the first reference for the G, okay, the second mass, and it is h. You see the h instead to this, and by calculating the h, it's equal L over 2 minus L over 2 cosine theta, and because theta is small, we can't write it like this. By replacing in both energy, in both expression of U gravitational, you see I put minus and not plus. Why? Because you can see in the picture that the current position is under the reference. The same thing here. The current position is under the reference. That's why we put minus minus. And U gravitational is this one, Now, U elastic is the same as previously, it doesn't change, and the U total is the summation, and we get this expression. And same thing, this L theta, you see that now the masses enter in theta square, because when we have the vertical equilibrium position, the are useful, the masses are useful to oscillating. Okay, it's different, and we use the same thing, quadratic form, by using the equilibrium condition, and we can cancel this term of theta, and we get this expression of U. And thank you for your attention.